Hello everyone, today we will learn the concept of logarithms with you all. When we were studying exponential functions, we once explained a problem where the annual growth rate of visitors to scenic area B in a certain place since 2001 was 0.11. After X years, the number of visitors is Y times that of 2001, representing the relationship between X and Y. It is not difficult to find that X and Y satisfy the relationship of exponential function. Y is equal to the power of 1.11, where X belongs to the left closed right open interval from 0 to positive infinity. So using this set of functional relationships, we can actually solve the problem of finding how many tourists have visited twice, 3 times, and 4 times as many as in 2001. This problem is actually 2 to the power of 1.11, 3 to the power of 1.11, and 4 to the power of 1.11. Solve the problem of unknown variable X. The essence of this question is actually to find the exponent by knowing the values of the base and power in the exponential formula. We have never learned such operations, but they are often used in real life. So, today we are going to learn a new calculation method, logarithm. For the analytical expression a, where the power of s is equal to n, a is greater than 0 and a is not equal to 1, find the problem of x. So we haven't studied this kind of problem before. So today we introduce new symbols to describe this new budget. If the power of s in 1.1 is equal to 2, then s can be written as s equal to the logarithm of base 2 with 1.1, and read as the logarithm of base 2 with 1.1. If the power of 2 to x is equal to 3, then x can be written as s equal to the logarithm of 2 to 3, and read as the logarithm of 2 to 3. Let's all think about it. Is the s power of 2 equal to n? I can naturally represent it as x equals. Read the logarithm with 2 as the base n as the logarithm with 2 as the base n. That's natural. If the power of x of a is equal to n, where a is greater than 0 and a is not 1, then we can naturally express it as x equal to the logarithm of n with a as the base. So, we introduced the concept of logarithms. Generally, if the power of x of a is equal to n, a is greater than 0, and a is 1, then the number x is called the logarithm of n with a as the base. Remember, x is equal to the logarithm of n with a as the base. A is called the base of the logarithm, and n is called the truth. We need to pay attention here. The reading of logarithms is based on as the base and n as the logarithm. Its writing should pay attention to its standardization and symbols. We specifically emphasize its symbol here. For the sign of logarithm, it is similar to the divisor in division operations, representing an operation that is used to connect the objects of the operation. Pay special attention. If a is the base and n is the logarithm, then the operation of finding the exponent of the base and its power n is called logarithmic operation. However, the sign of logarithmic operation is written before the number, and the result of the operation is a real number. Then we understand that, in fact, logarithms are operations for solving exponents, so there is a close relationship between exponential and logarithmic equations. Firstly, their base numbers are the same. The power in an exponential equation is also the true number in our logarithmic equation. The index is the exponent of the middle, which is both our logarithm and the logarithm of the middle. So now, we can use the equivalence relationship between exponential and logarithmic equations to consider the ranges of a, n, and x in logarithmic equations. Their base a satisfies the exponential requirement, naturally requiring it to be greater than 0 and not 1. And since the true number n is a power in the exponential equation, naturally n is greater than 0, and the logarithm is the exponent in the exponential equation, so x belongs to r. So by utilizing the equivalence relationship between them, we can generalize some important conclusions from exponents to logarithms. For example, we know that the power n in an index must be greater than 0. If the true number is greater than 0, then of course, when the true number is less than or equal to 0, there will naturally be no logarithm, abbreviated as negative and 0 without logarithm. Similarly, in the case where the base is greater than 0 and not unique, any number to the power of 0 is 1. So, the logarithm with a as the base 1 is equal to o. Similarly, the first power of a is, which I can simply refer to as the base. The logarithm of a must be 1. Next, let me introduce two special logarithms to you. We usually refer to the base 10 logarithm as the common logarithm, and denote the base 10 logarithm n as log n. Give two examples. we directly record it as log 5 with a base of 10 as the logarithm. We directly record the logarithm with a base of 10 as log 3.5. Similarly, in our daily lives, such as the capacitance-voltage relationship of chargers, the natural cooling relationship of objects, and cell proliferation, irrational numbers 2.71828 are often used to describe their natural laws. Using e to represent this irrational number, the logarithm of the irrational number e with a base of 2.71828 is usually called the natural logarithm, and the logarithm with a base of n is denoted as log n. For example, the logarithm with e as the base 3 is denoted as lane 3. The logarithm with e as the base 10 is denoted as lane 10. Let's take a look at example 1, exponential and logarithmic interconversion. The first set of 3 questions are all exponential, so our goal is to convert them into logarithmic equations. Let's take a look at the 3 exponential equations, whose bases are 5, 2, and 1/3 respectively. When converted to numerical values, the base remains unchanged and remains at 5, 2, and 1/3. Then let's take a look at the powers in the exponential formula, which are 625, 1 in 64, and 5.73 converted to logarithms, which are both true numbers. The exponents 4, -6, and m in the exponential equation are transformed into logarithms, so we obtain such a set of results. Based on 5, the logarithm of 625 is 4, which is our original exponent. Using 2 as the base, if 1/64 of the logarithm is -6, then this -6 is exponential. Taking 1/3 as the base, the logarithm of 5.73 is m. This is the letter m, which is the exponent. The same next group. This set of exercises actually aims to convert logarithmic equations into exponential equations. Let's go and discover it. The 4th question has a base of a half. What about the 5th question? Log 0.01 is equal to -2. That's a commonly used logarithm, naturally based on 10. The 6th question, lane 10, is approximately equal to 2.303, so this is a natural logarithm and can be considered base e. So we found their bases, which are half, 10, and e. Let's take a look at the logarithms in the logarithmic equation, which are -4, -2, and 2.303, respectively. Therefore, when we convert this logarithm into our exponential equation, it becomes an exponent. Now that we have determined the base and exponent, we will simply look for its power. What is its power? Nature is a true number, 16, 0.01, and 10. So we convert it to half -4th power equal to 16. The -2nd power of 10 is 0.01. The 2.303 power of e is approximately 10. Do you have any insights through practice? Although the logarithmic form and the exponential form are different, in fact, their essence is the same, because their bases should be the same, and the logarithm in our logarithmic equation is essentially an exponent, isn't it? True numbers are powers in exponential equations. So, for example 1, it deepened our understanding of the relationship between exponential and logarithmic equations. Next, let's take a look at example 2. Example 2 is to find the value of x in the following equation. Let's take a look at these 4 problems, which are all exponential equations. Therefore, the positions where x appears are in the true, base, and logarithmic positions, respectively. So, we haven't learned the operation law of logarithms yet, so it's quite troublesome to solve it directly. How should we solve this type of problem? We can convert it into an exponential equation. First, let's take a look at 1 and 2. The first question is directly converted into an exponential equation, where x is equal to the -2/3 power of 64. I can convert 64 to a 1/3 power of 4, and then we can use the properties of exponentiation to solve this problem easily. Therefore, this value is 1/16. The second question. We can convert this question into an exponential equation, where the 6th power of x equals 8. We need to note here that x is the base number, which has a range requirement greater than 0 and not 1. So, for x, I only require the arithmetic principle of this number, which is that x is equal to 1/6 power of 8. I can further convert this 8 to the 3rd power of 2, so this problem can be solved again by utilizing the exponential operation property to root 2. Next, let's look at 3 and 4. Log 100 is equal to x. If we convert it directly into an exponential equation, that is, the power of x of 10 is equal to 100, then we get that the power of 10 is actually the square of 10. Of course, x equals 2, the 4th one. The negative ln e squared is equal to x. If we convert it directly into an exponential equation, we won't be able to convert it. What should we do? We have discovered that there is a negative sign obstructing us here. So, multiplying both sides by a negative sign at the same time, the conversion from negative to positive is ln e squared equals negative x. That is, e squared equals negative x power of e. We have obtained x equal to negative 2. In fact, we found that the method is still a transformation, converting logarithmic equations into exponential equations, which further deepens the essential unity between logarithmic and exponential equations. So for logarithms and exponents, they are actually inverse operations of addition and subtraction, multiplication and division. Some students may have the question, why do we still need to learn logarithms after studying indices? Isn't logarithms just for finding exponents? What is the significance of the invention of logarithms? Then we have to start from its historical roots. In fact, in history, it refers to the invention of logarithms before the invention of exponents. In the 16th century, the rapid development of science and technology, especially astronomy, required a large amount of calculations for multiplication and division of large numbers. At that time, mathematicians lamented that there was nothing more headache-inducing for mathematicians than multiplication, division, square root, and cubic root operations on large numbers, which not only wasted time but were also prone to errors. In order to simplify numerical calculations, Napier published a book on logarithmic law using the corresponding idea in 1614. This corresponding idea can be described using a table like this. We can quickly calculate the value of 16 by 256 using this table. Firstly, find 16 and 256 in the second row. In the first row, find their corresponding values of 4 and 8 respectively. The sum of 4 and 8 is 12. In the first row, find 12, which corresponds to a value of 4096, which is the product of the two numbers. Similarly, we can also calculate the value of 4096 divided by 256. Similarly, if we find 4096 and 256 in the second row, their corresponding values in the first row are 12 and 8 respectively. The difference between 12 and 8 is 4. Find 4 in the first row, and the value 16 corresponding to 4 is their quotient. In fact, through such a table, it is very convenient to downgrade multiplication and division operations to simple addition and subtraction operations, which improves the efficiency of calculations. Yabble called this number logarithmic and described it in Latin. This Latin, in fact, is a combination of the Greek words relation remainder, which stands upright as a related number and reflects this corresponding idea. Mathematician Laplace once said that the discovery of logarithms extended the lifespan of astronomers due to its labor-saving nature. Okay, let's review the content covered in this lesson. Firstly, we have gained a preliminary understanding of the concept of logarithms and mastered the conversion between logarithmic and exponential equations. So of course, we also understand some important conclusions about logarithms and how to apply logarithms under the guidance of concepts.